Thanks everyone for joining today for another seminar from the Cambridge Ellis unit. Before we start, I would like to thank our sponsors for the unit. We appreciate their funding. Today we have Petar with us. Petar Veličković, I hope I pronounce it right. He's a senior research scientist at DeepMind. I think now maybe Google Brain, DeepMind, an affiliated lecturer at the University of Cambridge. Today he's going to talk about reasoning algorithmically from toy experiments to AGI modules. Petar he obtained his PhD in computer science from the University of Cambridge. He did his thesis under the supervision of Pietro Leo, and his research interests involve devising neural network architectures that operate on non-trivial structured data, for example, graphs. And he's also very interested in applications in algorithmic reasoning and computational biology. He's very well known for his work on graph attention networks, deep graph informatics, and many other relevant contributions. And yeah, I think that's all. Today he will be focusing on reasoning algorithmically, and I'm going to stop my sharing. I think Petar, you can share your slides.
Well, let me know if you can see them.
Yeah, that's right.
All right, sounds good. Thank you very much, Miguel, for the fine introduction, and thank you for the kind invitation. It is great to be speaking in front of the Cambridge Ellis unit again. As mentioned, my name is Petar Veličković. I am a staff research scientist at, well, what is now known as Google DeepMind, and I'm also an affiliated lecturer at the computer lab at the university also. And I'll be telling you about one of my current main research interests in machine learning. And specifically, it deals with teaching our best-in-class models to reason like an algorithm, and show how this starts from, how can this be an idea that grows from something that's a bit of like a toy, curiosity-driven question, all the way to something that might help us build generally intelligent agents. So let's get going. The context that I would like you to have in mind during this talk is one of classical computation. So this is basically going to be the backdrop to everything we're going to discuss today. And when I say classical computation, I mean the kinds of things you'll see in a typical undergraduate course in computer science. So the kinds of algorithms that allow you to sort a bunch of numbers, to find the optimal paths in a graph, to solve problems by breaking them down into sub-problems and stuff like that. So the kinds of things you might encounter in an undergraduate algorithms course. But also, because there is a deep learning backdrop to everything we're discussing, we're also going to be talking about how can we capture all of that classical computation with neural nets. And we'll even discuss to some extent, why is this even a good idea to begin with? So this is basically the backdrop of this particular talk. And this is not going to be just a technical talk. To some extent, it is also going to be a bit of a personal lens view of how my own views towards this topic have changed over time. And I feel like then, if we're going to embrace this perspective, it might be good to just start by the beginning. So like, what is it that drew me personally into computer science, and what is it that like makes me excited about this area directly? And for those of you who have done algorithms in classical data structures, you might have your own journey into this field. For me, the journey is via competitive programming. So basically, you can see here at different stages of my life, I have participated in various kinds of competitive programming contests, which basically ask you to write a program, an algorithm that solves something as quickly as possible and using as little memory as possible. And here you can see me competing in various stages, from the beginnings to high school to all the way when I was studying for my PhD at Cambridge, where I was part of this team of undergraduates, all from Trinity College, that won the first place on the ACM-ICPC Northwestern Regional competition, which is the Northwestern Regional of the most well-known competitive programming competition for university students. So hopefully this shows both why I have a vested interest in the area and also why I am competent enough to speak about it to you all today. And this shadow of competitive programming is something that follows me to this day. We recently filmed, if you're aware of Machine Learning Street Talk, if you're not, I highly recommend checking it out. It is a great series of just talks and interviews with machine learning researchers to give their perspectives on the development of our field. And recently we filmed the Machine Learning Street Talk episode in the computer lab to talk about this very research I'll tell you about today. And as part of filming this episode, the show host asked us out of nowhere to solve a hard lead code problem on the whiteboard, and he filmed us while doing that. So this is like a half-hour, video of me trying to solve one of these problems, which is already publicly available on YouTube. If something like this is of interest to you, do check it out. But otherwise, there will be a full Machine Learning Street Talk episode talking about everything that we're going to discuss today, but perhaps from a more philosophical lens as well. So if you find anything interesting, do check out this channel and subscribe to it and see what comes out in the near future. Now, of course, this is what brought me into computer science, and I would like to think that the story might be similar for many people in machine learning today. But I still wanted to do just that. This is what I thought my career calling was going to be. What changed was that in 2014, when I first reached out to my advisor, Petar Veličković, and I asked to do a project in bioinformatics for my undergrad final year. And I thought, bioinformatics is full of classical algorithms. This is going to be fantastic. But then what Petar told me is that you shouldn't do any of this algorithmic bioinformatics. You should just learn machine learning. That's what everybody seems to be doing in bioinformatics nowadays. And that's what led me to doing an entire PhD at Cambridge in graph nets. But I've never really forgotten where I came from. So in this talk, I'll tell the story of how I went full circle and combined my interest in classical algorithms with graph neural networks. So this will hopefully also impart some views about how my thoughts on these fields evolved over time. I'll introduce neural algorithmic reasoning, which is an emerging and exciting field of research that I'm personally quite invested in. And also, we will talk about how there's a perspective in which these techniques can lead to achieving generally intelligent agents in the future. So the main player, as I mentioned previously, is going to be the graph neural network. This was the topic of my PhD study and something I still heavily work with. This talk will not be an introduction to graph neural networks, really. If you want to see that, I've given lots of introductions on GNNs. You just have to go into YouTube and type my name and put GNNs. You'll see a lot of videos that you can look at. For the purposes of this talk, I just wanted to make sure that we all have a basic high-level understanding of what a graph neural network is. And effectively what it is so you have some data defined on a graph. So there's a graph structure with feature vectors in the nodes, so XA, XB, and so on. And now a graph neural network literally just takes one node and all of the node features in its immediate neighborhood, and based on that set of neighboring features, updates the features into some latent space H. And that's it. Like, this is just some function that operates over the set of neighbor features. And in order to be a legitimate graph neural network, it needs to be invariant to permutations of those neighbors. So regardless of how I choose to present the neighbors to the function, it should give me the same result. And there's many strategies in which you can build these local functions F, but one very popular strategy is the message passing strategy, where effectively here you have the node B and you have all of its neighboring feature vectors. Each node and its neighbor collaborate to compute a message vector, M, and that message vector is then sent across the edge, and the receiver node combines them together to get the updated representations. As long as this function that you use to combine the messages, this O+, is invariant to permutation, so it doesn't depend on the order in which you send the messages, this is a valid graph neural network. And this O+ can be anything which is independent of the order of the inputs, so something like sum, average, element-wise max, all of these are valid choices of O+. So this is as far as I'm going to go in terms of GNN theory. Hopefully this gives you a nice bird's eye view on how we build these kinds of functions. And I will just say that this function that I show you here on this slide is incredibly general. Like, you can use this function to express basically any state-of-the-art neural network architecture today, including the transformer, right? So this is our starting point. Now, after I finished my PhD, I started working at DeepMind shortly after in January 2019. And there I met Charles Blundell, who I co-authored many papers with since then. And there's a good reason behind that, because Charles and I are both computer scientists by training, and we had a lot of really fun first discussions, which led to asking some very curiosity-driven, but at least initially inconsequential questions, such as the question that started it all, really: can graph neural networks learn to execute these classical algorithms? And what this means is, if I give to a graph neural network as input a graph which specifies a particular problem I would like solved. So in this particular case, say I might want to find all the shortest paths starting from the node I tagged with 0. Can I now build a machine learning model that first embeds those features into a high dimensional latent space, H, then run a graph neural network over that latent space to update the representations? Can I then decode from that the exact shortest paths in this graph, which are the edges tagged in gray? Can I learn to do this? Like this very well-defined artificial problem. Now, initially, I must stress, we designed this as a way to benchmark the expressive power of neural networks, really. So it was really a question of, can neural networks do this? And we thought it was a pretty good setting to study such problems because, first of all, we get lots of perks that we don't get in most other machine learning scenarios. The first one is infinite data. You can generate as much inputs as you want, knowing what the function is that you want to imitate. But that function itself is still fairly complex. Like it takes a lot of local manipulations of data to get from input specification to shortest paths. Like this requires a complex data manipulation. And the generating function is very clearly specified, which means some endeavors like interpretability or explainability are going to be much easier to do because I know what is roughly the target I would like my network to learn. But I must stress that this was really the extent to which we were thinking about this, right? We were just thinking about, can we teach how well can existing models fit these kinds of problems, and not much more than that. So the real kind of high-level question we were starting to ask ourselves is, what makes a neural network model better or worse at fitting certain classes of algorithmic tasks? This is really the first question. And it was very convenient for us because there was concurrent theoretical work that already started to progress towards this. This came from researchers at MIT, and they've coined this phrase algorithmic alignment. Now, how can I explain algorithmic alignment? Basically, here I have 3 standard techniques to build neural network models. The MLP, which just concatenates all the features of everything you have without any regard to their structure. Then there's deep sets, which are explicitly mindful that your input might consist of a set of objects, and then you can transform each object separately and then aggregate the results. And then there's GNNs, like we just described them, which also explicitly take into account the pairwise relations between the objects. And you might be wondering, what kinds of tasks would these different architectures be able to fit? It turns out that you can even mathematically formalize and prove a theorem on what makes an architecture better for a task. And when I say better here, I mean sample complexity. So you're going to need fewer training examples to fit it to a certain level of error like epsilon. And this theory was proven by the researchers from MIT in this paper, What Can Neural Networks Reason About? And the theorem that they've proven basically says, if you have better algorithmic alignment, you're going to generalize better. What this algorithmic alignment means is that I can chop up my algorithm into parts, and those parts line up nicely with functions or modules in my neural network. Now, this begs the question of, what would graph neural networks align to? And I think this is something that's best represented by a picture. Specifically, in this paper, the authors showed that graph neural networks align with the strategy of building algorithms known as dynamic programming. For those who know about it, you'll already know it's a very powerful paradigm. You can use it to express large quantities of polynomial time heuristics or even more expressive heuristics. And it's a very general, powerful paradigm of how do you solve a problem? You break it down into subproblems, and then you aggregate the results to get the full solution. So I think this is once again best represented using the picture. On the right-hand side, you have the equations of the message passing neural network, as I told you about them before. And on the left-hand side, you have a standard dynamic programming algorithm for finding shortest paths, the Bellman-Ford algorithm. And how does it compute shortest paths? It maintains a variable in each node called du, which tracks what is the optimal distance to that particular node. And how do you update it? By the minimum of dv plus weight from v to u. What does this mean in layman's terms? It means the optimal path to reach me is the same as the optimal path to reach one of my neighbors and then take a step from the neighbor to myself, right? That's literally what this equation is encoding. And you can see there is a clear correspondence between the equations of the graph neural network and the equation of the dynamic programming algorithm. The d variables can be seen as node features. The process of adding an edge weight can be seen as computing the message function, and the aggregation of all of the distances from the neighbors can be seen as the aggregation function, the O+ of the graph neural network. So hopefully you see on this simple pictorial example how graph neural networks tend to be very well aligned to this idea of sub-problems and combining solutions from sub-problems. And the authors didn't stop at the theory. They also empirically evaluated this, where you have progressively more challenging versions of tasks, where initially a deep set was also potent, but MLPs are not. And then gradually you have problems where not even deep sets can handle them well. And then dynamic programming algorithms where GNNs, as you increase the number of layers to approach the theoretical requirement for the number of layers, line up with the algorithm performance much better than any of the other candidates. Now, what did this mean for us? Well, we already knew we wanted to use GNNs for our investigation. This theoretical result just made us even more confident that we should do that. And that led us to our first paper in the area, Neural Execution of Graph Algorithms, which we published at iClear in 2020. So what did we have to add? What value did we have to add to this already very interesting theory? Well, TLDR, algorithmic alignment, is indeed a super powerful tool to choose which architecture to use, but it doesn't really allow you to be reckless, if that makes sense. You cannot, this doesn't mean you can just take any GNN, throw it at any algorithmic problem and expect good results. You need to be a bit more careful. And our paper shows you how to be more careful effectively. So what I'm trying to say here is that even though GNNs might be the right class of model for algorithmic tasks, you cannot just do this on any task and expect good results out of distribution. So what do I mean by this? I mean, if you run your graph neural network that was trained on some algorithmic data on an input which is, say, much bigger or very different from the distribution that you have in the training data, you should ideally expect your model to work really well even on those inputs. So generalize out of distribution, extrapolation, right? This is something that's very different from, say, a standard machine learning application where you might have a test set which is somehow relevant to the distribution of your training set. Here, any self-respecting algorithm should work well no matter what input you give it, right? So with algorithmic reasoning, we really care about how will the model perform on inputs that are very different from the inputs you see in the training data. That's arguably a critical property of a reasoning system. Anything else is just fooling you by kind of capturing statistics of the training data in one way or another. So if your model truly learned how to behave like an algorithm, it should work across a wide variety of inputs, not necessarily just ones captured by the training data. And if you're not careful, your GNN will very trivially overfit to any distributional parameter of the inputs that you have in your training set, and thus sidestepping the actual algorithm it's trying to execute. It's actually going to learn something completely different. And that's not particularly useful in this particular context. So in our algorithmic execution paper, we make several observations on inductive biases to put in your GNNs so that you can perform better. And this allowed us in that specific paper to generalize to graphs that were 5 times larger than the training set graphs for 2 specific pathfinding problems we looked at. The specific architectures studied by the MIT paper were not capable of generalizing to this size. In fact, I think a lot of them ended up numerically blowing up. So what were some of our key insights? The first one, the work from the MIT paper had unshared GNN layers. And I think this is quite problematic if you want to do execution, because as the inputs become bigger, your algorithm might need to make more steps. So any kind of unshared layer isn't really a good idea. So what we do is we have one processor network GNN, we share it, and we run it for some number of steps. This now allows us to run it for an arbitrary number of steps at test time if we need to. And it also nicely captures the assumption that the algorithm is iterative, right? So there is one particular iteration that keeps repeating until you're ready to decode the outputs that you care about. So that was the first procedure, the sharing of the intermediate layer. The second, which when you look at it, might seem very intuitive and very simple, actually was a bit of an uphill battle. So we showed that obviously you look at this alignment picture from before, you might want to use an aggregation function that lines up with what your algorithm is doing. That sounds like a fairly trivial choice. So we use the max aggregation to really help our models capture this thing better. But I must stress the use of max aggregation at the time in the year 2020 was seen as a rather controversial decision, because there existed previous expressive power results of GNNs that showed that max is a strictly weaker aggregation than average, which is a strictly weaker aggregation than sum. Like it can represent strictly less functions than sum can. However, just because something is more expressive doesn't mean that you should use it in all cases. And in this case, it didn't matter that the max aggregation would compress some graphs into the same representation. If they had the same shortest paths, that's fine, right? So in this particular case, the choice of max really made sense. And even though at the time it was contrary to folklore, we now have many solid theoretical papers showing why using max is a good idea in this case. So we've kind of crossed that threshold, but it was a bit of an uphill battle. The third one is in machine learning, you often have inputs and outputs, and you have the loss function on the outputs to fit your model. Well, in algorithms, you have an extra amount of data that you can leverage to even more closely line up with what the algorithm is doing. And that is often there are intermediate results that the algorithm has, which are interesting to fit. Say in the context of a shortest path algorithm, after k steps of a shortest path algorithm, you should be able to predict shortest paths that use no more than k hops from your source node. And we can supervise the model to decode those paths after k hops. So this now gives us extra supervision signal and an extra method to kind of steer the model towards what the algorithm is doing. Now, I must stress that while these ideas might seem interesting, the idea of algorithmic alignment from an intuitive level isn't particularly new. There were many previous architectures that took lots of inspiration from computer science constructs. And maybe the best example of this is the neural Turing machine and differentiable neural computer, which was a paper from DeepMind that proposed a Turing machine-inspired neural network that even landed in the journal Nature in 2016. So it was quite well recognized. And it was decisively influential because if you look at the way the neural Turing machine tried to emulate random reads and writes into a memory cell, they ended up discovering content-based self-attention 3 years before the transformer paper, right? So a lot of really influential ideas came around just from being able to analyze things from a computer science perspective. However, as you know, you don't need to be told, you know this really well, nobody really uses neural Turing machines anymore. And why is that? Because they introduced a lot of these components at once in an effort to build a differentiable computer all at once. And therefore, it was really hard to do credit assignment and debugging of when it fails, why is it failing? And whenever you took it even a little bit away from the specific benchmarks they used in the Nature paper, a simple recurrent neural network was often beating them, right? So what's different about our work? We don't try to replicate an entire computer at once. We try to carefully search for inductive biases that are relevant to certain classes of computation and carefully, theoretically, and empirically investigate whether adding that one component at a time makes sense. And this seems to be a more successful approach so far. And we can keep playing this game that I just showed you. You can keep trying to align GNNs to different classes of computation. And now we have several top-tier conference papers that showed how you can align with n-log-n linear arithmetic algorithms, iterative algorithms, pointer-based data structures, and even persistent auxiliary memory. So there's lots of different computer science constructs that you can put into a GNN. They all lead to slightly different GNN rules that align better with different kinds of tasks. So it seems like to get good out of distribution generalization, you should play this kind of fine-grained alignment game. And eventually the theory caught up to these insights. And now we have several theoretical papers like linear algorithmic alignment, causality-based alignment, and category theoretic formalizations that further kind of show the theory catching up to these empirical models. So unlike maybe some other areas of deep learning in algorithmic reasoning, the theory and the empirical parts are sort of keeping up with each other at a reasonable pace, let's say. But of course, so I showed you a few relevant papers and a few interesting architectures that do fine-grained alignment to a target algorithm. And this is all nice, and I think it answers for a good part our initial question. But now it's time to get real, right? So why not just run the target algorithm? Because I write up a paper like this, I'm really happy about it. I send it to a conference, and then I see reviewers writing the kinds of things you see on this slide. What is the purpose of learning how to execute an algorithm? Why not just run the target algorithm itself? And my personal favorite, I'm actually quoting this reviewer. This paper will certainly accelerate research in building better algorithmic models. There's certainly a lot of research that would make advantage of it. I'm just not sure this research should even exist, right? Like, it's a fantastic thing to read as the first author of a paper or something like that. And, it's just, you can say all kinds of things about this, but let's just put my ego aside for a second and try to think, is there some good reason in why we're getting these kinds of reviews? I would say there was a good reason, because there is a point in which tautologically, the algorithm you're trying to fit will always execute itself better than any GNN you learn on top of it. So up until this point, we did this curiosity-driven exploratory benchmarking, But these reviews were really telling us we need to prove that doing this is actually useful, that it actually leads to something beneficial. And in the process of our developments over the past years, we came up with several ideas to do this. And I'll present to you the 3 that, in my opinion, saw the most impact. Okay. So the first point I would like to mention is that these algorithmically aligned models are capable of accelerating science. And if you want to see evidence that algorithmically aligned models are capable of accelerating science, I invite you to look no further than the cover of Nature. So this was a paper that, along with several co-authors from DeepMind and mathematicians from the universities of Oxford and Sydney, we have developed over a multi-year period where we used these algorithmically aligned graph neural networks to uncover the hidden structure inside huge, large-scale mathematical objects, certainly too large for mathematicians to analyze with the naked eye. And then based on these explanations from our models, the mathematicians were able to derive new conjectures, prove new theorems that broke new ground in 2 very disparate areas of math, representation theory and knot theory. And the significance of this was recognized by the journal Nature, which then placed our work on its cover page in December 2021. And it also got a fair amount of media coverage, like this New Scientist article. But like, I personally find all these things to be a little bit inconsequential. What I find a lot more telling are the anonymous reviews we got for this work from professional mathematicians. And these are just some of the things that the reviewers wrote for our work. Now, I need to stress, this is anonymous peer review for Nature. Like, these people are supposed to help us find things that are not so good about our framework, right? But you see these mathematicians basically saying, this paper marks the beginning of a new phase of use of computers in math research. I cannot imagine a mathematician not using these methods if available to them, because not using them means progressing much more slowly. And what I also particularly liked, the 2 separate mathematical experts claimed that our mathematical contributions were good enough to be publishable in the top tier relevant journals in those areas of math. So you might have this one Nature paper, but really it hides inside it 2 top tier mathematical journal papers. And I'm very happy that, like, several months since this paper came out, we actually were successful at publishing both of these papers in top tier mathematical journals, including this one over here that was published in the journal Representation Theory, which I am very happy about this one. It helps me tick off a huge item off of my bucket list, because it was always a huge dream of mine to publish a math paper. But I always had this problem in that I did not really know math. So this was a great way in which I could use my other skills to help mathematicians make a paper like this, which still makes me quite happy. Now, a little bit about what we actually did there. So we took a GNN and we trained it to fit a mathematical data set, from some input graph to some output representation. And then we used some very simple gradient-based saliency methods to try to explain what were the subgraphs that are most interesting, right? So now a mathematician doesn't have to look at this massive graph like the one in the bottom left. A mathematician only has to look at some subgraphs like these diamonds at the bottom, and that's usually much easier to analyze. Now, of course, I must stress, our explainability method was not as sharp as what you can see here. It did not really detect just those diamonds. It detected the diamonds and maybe some extra noise on top of that. But still, analyzing a small noisy graph of 10 nodes is much easier than analyzing a huge graph of like 1,000 nodes, right? So we still helped the mathematicians find the right pattern in this sea of potential edges. And using the signal, they indeed proved new theorems and derived new conjectures, and basically found structures that propelled the development of math even in the recent months. Now, but there is a question, like, while we could fit a GNN to a mathematical dataset, which GNN should you use to fit this mathematical dataset? There's lots of variants, and the basic standard expressive GNNs did not give us any useful signal like this. So the best results were actually obtained by an algorithmically aligned GNN. And what do we mean by this? Our math collaborator, Jordi Williamson, showed to us in a few math lectures how can we compute the outputs he cares about if we had privileged data in the nodes of the graph. So that's this algorithm you see on the right-hand side here. You see it feels quite a bit like a GNN. There's some kind of summation over neighboring states, right? Followed by some activation function, this tau over here. So that looks very much like a GNN, but it has a very specific equational form. So then, okay, maybe we don't have access to these special node inputs, but let's try to make the GNN as close as possible to that equation. Let's algorithmically align it to what that equation is doing. And by doing that, we actually got the performance we needed to get those explanations. So more generally, what does this mean? if we have a target algorithm that exists, but it's inapplicable because the inputs are privileged, algorithmic alignment might allow you to embed the priors from this algorithm anyway, even though you don't have access to the inputs to that algorithm. So that's the first story. The second story, which we recently published at NeurIPS with some collaborators from ETH in Zurich, is the idea that algorithmically aligned models can make fast heuristics. And what do I mean by this? We studied this from a computer networking angle. I am personally not a great computer networking expert. I have done one undergraduate course on it, so I don't know that much about it, but I understand it on a high level. And surely we can all agree that computer networking is very important because its protocols underlie the entire internet, right? So one very important problem that apparently a computer networking practitioner has to solve is they have access to these kinds of specifications that you see on the right here. So that's just a list of constraints that the computer network needs to satisfy. Which routers should talk to which other routers, how quick the path should be, what should be reachable, what shouldn't be reachable, and so on and so forth, because of security concerns or whatever. So the task of the practitioner then is to do configuration synthesis, which is to compute the graph of routers, this configuration W. How will the different routers in the network be connected, with what signal strengths and stuff like that, such that when I run a particular networking protocol, like a message passing protocol between the routers, the resulting forwarding plane I get is consistent with the constraints, okay? Now, it shouldn't come as a big surprise that finding these configurations from the specification is an NP hard problem, and solving it practically basically requires you to use slow SMT solvers, which are doubly exponential complexity, right? So it's really, really bad scaling with the number of constraints and the number of routers. So here we wanted to investigate, can we speed this up somehow by going directly from the specification to configuration using a graph neural network that's algorithmically aligned. And effectively what this means is we're trying to invert this protocol arrow over here to go from configuration straight into, from specification straight into configuration. And obviously to do this, we need to build a data set of spec to config. And how did we do this? Well, we follow the protocol to get kind of an inverted data set in a way. So we start with random topologies of these routers, randomly generated and randomly chosen configurations of them. So this gives us the targets for our machine learning task. Then we run the protocol to get the forwarding planes. And then we extract all the things that are true about this forwarding plane to get a set of constraints. And those are our specification inputs, right? So that's how we build our data set. And how do we then turn this into a graph problem? So say we have this particular input set of specifications. What we do is we randomly mask parts of it, right? So we put these question marks to certain parameters, and then we will ask the GNN to fit these masked parameters, right? So we can turn this specification into a graph by just treating each router variable as a node, each edge variable as another node, and basically connecting them to follow the logical structure of these facts. And we'll put question marks on all the relevant features that we've masked out, right? And now we just run a GNN on top of that to predict the missing, to predict the things that have the question mark. So in this particular case, it predicts that the connection parameter here should be 12, for example. And that's it. This is how we train this model to satisfy the constraints that we have. And I mean, it should come as no surprise because this is a forward GNN that goes straight from spec to config in a polynomial time that is going to be much, much faster than the doubly exponential SMT solver. And in fact, in some regimes like 16 requirements and up to 18 routers, it is over 490 times faster than the doubly exponential solver. Now, of course, there's no free lunch, right? Like you cannot get all those improvements and speed up without sacrificing anything. And specifically what we sacrifice is the accuracy. So we're not guaranteed to find perfectly correct configurations. However, we then led an analysis to see how often are the constraints actually satisfied. And even in the most dramatic regimes, the average number of constraints satisfied is still over 90% of all of the constraints. And this was deemed by our networking collaborators to be a good level of consistency for downstream human in the loop use. Like it's accurate enough that a human can take this partially consistent assignment and then manually tweak the rules and run the solver again and so on and so forth. And the reason why this is good compared to, say, the SMT solver is because even though the SMT solver would give you a correct solution, humans are not perfect at writing these specifications anyway. So the first spec you write might be over constrained and might not even have a satisfying solution. So you're going to spend a doubly exponential amount of time to find out that what you built doesn't have a solution. And then you have to start over anyway. So you have to do iterative stuff regardless of which solver you use. You might as well use a fast but reasonably accurate one. And that was the main takeaway from this one. And maybe more generally, what this means is that here we have a target algorithm, which is very complex, so we can only approximate it, but we can approximate it in such a way that it gives us a fast and accurate heuristic, enabling rapid human-in-the-loop iteration. Okay, so now that I've mentioned these two specific application areas, how we use the algorithmically aligned models there, let's talk a little bit about the neural algorithmic reasoning framework, which is maybe a more general step. So it's a bit more of a scientific pursuit, but it's hopefully one that could lead to pretty fun returns in the future. And if anything that I mentioned today makes you more interested, we, together with Charles Blundell, I published a position paper on this topic in Patterns in 2021, which should hopefully give a lot of very cool explanations on all of the stuff I'll tell you here without going very deep into math. So it's a very accessible kind of introductory text about this, this area. And to get you thinking about neural algorithmic reasoning, I'll actually prime you with a relatively simple example, which is find the optimal path from A to B, okay? Now, this is something that in a computer science class you hear all the time. And if you are a computer scientist and you see a question like this, chances are 9 times out of 10, you will respond to this question in a very singular way. I know that I would always, as a computer scientist, I would always respond in a very singular way, which is I'm going to assume that what you're asking me is that there is a weighted graph with like a scalar distance in every single edge, and I'm asking you to predict shortest paths in that network. So I can take my abstractified graph and run my Dijkstra's algorithm on top of that and get the shortest paths. But, you know, there is nothing in this question that says, you know, my inputs are weighted graphs with scalar weights, or that optimal paths means shortest paths, right? So what happens in reality is we all get very excited about this approach, but really it's hiding a real world problem underneath it, right? Like, and I've learned this on the first instance when I worked on the project that put graph neural networks inside Google Maps. So one thing that you might also know me for is when you take out Google Maps and you ask it for how quickly can I go from point A to point B, anywhere in the world, including Cambridge, the travel time estimate that you get is served by a graph neural network that we have developed in collaboration with Google. But you know, there you learn just how complicated this problem is. It's nowhere as simple as running an algorithm over a given graph, because Google Maps does not have access to graphs. And what's more, the real world road network is not a static graph, right? There's lots of things that dynamically change the properties of the network, like traffic jams, roadblocks, traffic lights, weather conditions, all sorts of things that may or may not have a huge influence on the flow of traffic. And also the data itself. The data itself doesn't look like this nice graph in the middle. You might notice the way Google Maps collects data about the movement in traffic is you have these phones of yours, right? They sit in your car, and the way the phones move, that tells Google Maps how quickly the traffic is roughly moving. But this is obviously super raw, super noisy data that might be wrong in all sorts of ways. And what's even worse, you might be very adversarial about it. You might have heard about this experiment. I'm not sure. I think it happened in Belgium, where a guy put 100 phones in his sack and he decided to walk down the street with his sack and basically convinced Google Maps to route everybody away from that street. Like, this was a very famous adversarial example. I think even Google blogged about it at one point. So just to say, like, you're in an environment where not only your graph is not static, but your data isn't lined up with the graph, and the data itself might be noisy or adversarial. So in this setting, what can you do to run the algorithm, right? There needs to be something that helps you cross that divide from the raw data to the data that the algorithm will accept. And traditionally, this is done manually by humans, either by manually mapping the data or by writing a heuristic that will map it for you. But it's still done by a human feature engineer. And this obviously begs the question of, can humans ever hope to manually do this mapping accurately? I would say from the 1950s, we knew the answer to this question was no. Now, here is one very nice illustrative paper, which looks at studying the max flow problem, which is a very popular problem in theoretical computer science. And they look at it from the perspective of evaluating the capacity properties of railway networks. And at the very start of this paper, they have this very nice paragraph, which I quote in full, where they effectively say, even when you're intimately familiar with the railway network you're evaluating, the final capacities that you put as input to the algorithm, so the actual number of trains that could pass through every railway link in a certain amount of time, it's something that's more of an art than a science. There's no known mathematical model that can help you pick this. You have to sort of pick it based on judgment and experience, which humans are not always good at, right? So this is a pretty important problem because there's a divide between the classical algorithm and the real world task they were designed to solve. And if you want to satisfy the strict preconditions of the algorithm, it may lead to you drastically losing information. Or put succinctly, it doesn't matter that your algorithm is provably correct if you run it on wrong inputs. It just doesn't matter at that point. And what might happen is even worse than this, if you might have partially observable data. So there are some parts of the input for the algorithm which you don't even have. What do you even do in this case? So what I'll show you in the remainder of this talk is how we could attack this problem by what I like to call neuralizing the algorithm. Now, what do I mean by neuralizing the algorithm? Well, okay. What we said initially, there was a problem because there was a manual feature engineer in the pipeline that took raw data to the algorithmic inputs. Okay, well, remember what made neural networks successful in 2012 onwards? It was that we replaced manual human feature engineers with neural networks. So let's do that. Let's replace the feature engineer with a neural network. So now a neural network maps the natural inputs to the algorithm. And now you train this whole thing using gradient descent over the inputs that you have. Now, you might be wondering first, hang on, can we even apply gradient descent if this algorithm is not differentiable? Well, that used to be a problem, but I would say there's some really cool research published over the previous few years that showed really nice ways to backpropagate through basically black box combinatorial optimizers. I particularly like the work of Marin Vlastelica and others that was a spotlight at iClear a few years back. But basically, there's a huge body of work that to more or less extents solves this problem, even for completely black box algorithms. So this, I would say, is not as much of a problem as it was. There is a more deeper problem, though. And the problem is that this pipeline of ours strongly commits to using the algorithm. Once you compute the inputs, you're done. Whatever comes out of the algorithm, you trust. There's no way to revert any mistakes that might have been made. And this leads to a bottleneck problem, which we like to call the algorithmic bottleneck. Informally, even if you have insufficient training data to properly estimate these inputs accurately, you're going to hit the same problem as before. The algorithm will give you correct solutions in an incorrect environment, so they might not be that useful. And what if you need to run more than one algorithm? What if there is something that this one algorithm does not explain completely, and so on? So there's lots of issues with strongly committing to just one algorithm. And how do neural networks avoid strongly committing to something? They just stay high dimensional throughout, right? So neural networks are not bottlenecked. There are vectors that are maintained throughout the pipeline. And if any component of that vector is badly predicted, you still have other dimensions that could save you in principle. So to break our bottleneck, we will replace the algorithm with a processor network P. So now we still have an encoder network that maps our raw data into some algorithmic state, but now that state is high dimensional, this latent state Z. And the processor network just updates that latent state without losing dimensionality, such that at certain points, you can then decode the outputs you care about by using a decoder network. So this is the general principle we're going to use. And this, if you do this correctly, this is fantastic because this fixes all of the problems. It's differentiable end to end. There's no bottlenecks. Everything is high dimensional. And in case you do have more than one algorithm to explain, if there's anything P does not explain, you can just skip it by adding a residual connection, right? And that now fits anything that P cannot explain. So it answers all those 3 points. But of course, it rests on there being a processor network P that accurately aligns with the algorithm. So how can we get those models? That is the remaining question to answer. Well, if you remember that pipeline I showed you before of how we use encode, process, decode to train a model to follow steps of algorithms in a benchmarking sense, well, here is one example of how that can actually be useful. This is our neural algorithmic reasoning blueprint. Imagine now you have a real world problem you want to solve using that algorithm. You can use this pre-trained processor network as a sort of differentiable high-dimensional algorithm, and you just latch it onto any neural pipeline that maps your raw inputs to raw outputs. And suddenly, you're now able to basically apply the algorithm to your raw data without ever mapping that raw data to the bottlenecked form. And this hopefully fixes the problem. So you pre-train the GNN on the algorithm, and then you deploy it on the natural task that you care about using these new encoders and decoders F tilde and G tilde. And this now, as we quote from our paper, allows you to run classical algorithms on inputs that were previously considered inaccessible to them. And this used to be just a proposal, but now we have several proofs of concept that the idea works that were published at several top-tier conferences: XLVIN, SNAP, RMR, and DAR. I'll just show you a tour of a few of those. XLVIN was the first one we built, where we tried to improve reinforcement learning agents by giving them access to the value iteration algorithm. Value iteration, you might know, is an algorithm that perfectly solves any reinforcement learning environment, but you need to know the whole graph of states and actions, which very often you don't know. So what do? We take some normal input you would expect in an RL problem, like this picture of an Atari video game. You embed it into a vector that represents it. You learn a self-supervised transition model to kind of expand the local graph of all the neighboring states after taking all possible actions. And then you run a graph neural network that was pre-trained to execute value iteration on this graph that you just built. And this now gives access to a more data efficient agent that's able to some extent, leverage the value iteration algorithm and what it's doing. Then you have RMR, which looked at these problems of, in a self-supervised way, learning to predict future states of these images of bouncing balls. So your inputs are bouncing balls, and you have to predict the dynamics in pixel space. Well, you know that there's a very simple physics underneath this thing, right? If you're able to go from pixels to individual representations of each ball, like radius, position, velocity, then it's just a simple physics rule from which you can render back the scene. But of course, this physics rule is bottlenecked, like we just discussed. So we applied the blueprint in our RMR paper, where we first teach a GNN to fit how these trajectories of balls go in the point space. And then we take that pre-trained GNN and stick it to a vision architecture that simulates how the balls move in pixel space. And this allows us to take the specific priors inside the physics model and put them inside the image-based model. And lastly, the DAR, which we will be presenting at iClear next week as a spotlight talk, allows us to have dual algorithmic priors. So we train a model to execute dual algorithms, max flow and min cut here specifically, by one processor network. And then we did something which haven't tried before. We scaled it up to really, really large graphs. Specifically, we looked at these graphs of mouse blood vessels in the brain. And you have to classify these vessels for whether they are veins, capillaries, arteries, right? Now, I don't know that much about the blood system and the mouse brain, but I do know that the purpose of blood vessels is, in principle, to conduct blood flow. So if I know a flow algorithm, it might help me answer those classification problems better. So we pre-train how to execute max flow and min cut on 16 node graphs. Then we use that pre-trained model without any changes in a 180,000 times bigger mouse brain graph. So from 16 nodes to millions of nodes. And it gives us a clear representational advantage, 5 to 6% accuracy improvement over a state-of-the-art baseline. So it was pretty important, these additional features that we get from the algorithm. Now, the last question I want to address before leaving the floor for questions is, where can we get these good processors from? Because all of these scenarios I gave you so far involved a domain expert who understood there was an algorithm that needed to be applied somewhere, and the computer science expert who had to build a data set to train the GNN on for this algorithm. And I hope you agree with me, it's a huge barrier of entry. Like, if you don't have a computer scientist on your team, you won't necessarily know how to properly build this data set and align the GNN to it. So how can we reduce this barrier of entry? How can we get a good collection of processors without requiring people to have prior domain knowledge? And for inspiration, we looked at this classic book, the Introduction to Algorithms textbook. It should hopefully be familiar to most of you. It is the textbook used for teaching undergraduate algorithms and data structures, including at Cambridge as well. And it's called CLRS in homage to the first letters of the 4 authors. And even though it's a couple thousand pages long, it only has about 90 algorithms. And these 90 algorithms serve as a sort of basis for a career of a modern software engineer. So if we could teach a model to execute those 90 skills, that would be a pretty good basis to start from, regardless of where you apply them, right? So, well, in our first version, we only exposed 30 algorithms, so not all 90, but you'll see that they do span a whole range of irrelevant skills like sorting, searching, pathfinding, dynamic programming, string matching, and even geometry, so finding convex hulls or intersections of segments. And we made this data set fully publicly available. You can find it on our GitHub page. There is a companion paper we published at ICML, and you can readily now experiment with these models yourself. And what's cool about our benchmark is that we don't just give you inputs and outputs to these algorithms, but we expose the entire intermediate trace, so you can truly learn the dynamics of that algorithm. So in the case here, you have insertion sort, sorting a list 52431. You see, normally you'd only have the graph on the left and the graph on the right, which is fully sorted. But our benchmark code exposes all the intermediate states automatically and builds loss functions and baselines to automatically fit them. So all you have to do is specify the specs of your algorithm and the generator for the inputs, and everything else is taken care of by our library. So you can think of CLRS as not just a data set, not just a baseline, but a data set and baseline generator, which I think should make it really useful for future uses of algorithmic reasoning models. And this now then begs the question of, if we've taught a model to execute one of these skills, why stop at one? Could we learn to execute all 30 of them? Also, we kind of promised we would do it. There was this article where we were interviewed, Charles and I, by a journalist, and the journalist decided to take out of context this sentence that DeepMind is developing one algorithm to rule them all. So we had no choice but to follow up on that promise now, right? Well, jokes aside, we wanted to build a system like this, a single processor that has a single set of weights, but it's capable at the same time of doing a sorting task, doing a path finding task, doing a convex hull finding task, and so on. The only thing that would tell these tasks apart are the different encoders and decoders, but we deliberately make these functions linear so that they do not overwhelm the processor. So most of the computation is still happening inside the processor. The F's and G's just serve to map in and out of the latent space. But this is not as easy as it sounds. And in fact, to get a good generalist multitask learner, you first need a very stable specialist model that fits just one of them. And we had a very long kind of 2-month sprint to try to find all the different ways in which we can make the single task models better. And here, like, I'm just quickly going through the bucket list of all the things we added. You'll see some of them involve teacher forcing, changing initializations, changing the update rules, including things like the sinkhorn operator to get valid permutations, gating mechanism, triplet reasoning, lots of very interesting additions that carefully algorithmically align us more to these single tasks. And taking all those things together, we got one single task executor on the right, which was over 20% better on average than any previous state-of-the-art model we had on these tasks. I must stress these are 4 times bigger graphs than the ones you have in the training set. So it's testing out of distribution generalization. In distribution, these all solve to 100%, right? But it's out of distribution that we care about. And with this level of stability, we were now able to train just one of these models in orange to match the performance of the single task 30 specialists in blue. And you can see on some tasks, the generalist is better. On some tasks, it is worse than the specialist. But on average, the plots you see on the far right, the generalist and the specialist are indistinguishable in terms of average performance. So on average, we have one generalist that matches the 30 specialists. And we also did a huge ablation. There's 3,000 experiments on this one slide, which show how when you gradually remove all those tiny things we added, the performance becomes worse and worse. So every single thing we added actually makes sense for the final architecture. And we wrapped up our results in this paper, A Generalist Neural Algorithmic Learner, which we published at Log 22 as a spotlight. And we believe it's a reasonable success to our initial aims. And to check whether it was truly successful, let's ask the public. Let's ask Reddit. We went on our Singularity. We asked for some, we looked at some of the comments people had on our paper. And, well, it's not new. Others tried this too, but our model has a lot more success, which is nice. This is a pretty big deal because, as they also have formal training in psychology, this is close to one of our guesses as to how a brain works. I'm not particularly versed in psychology, but I like this idea. Remember how GPT-3 impresses with fluent writing but makes blunders in arithmetic, logic, multi-step reasoning? This could be a way to incorporate reasoning into such models to reduce these blunders. I tend to agree with that. And my personal favorite, if you think of AGI as a car, right? Gato, the DeepMind model that executes multitasks at once, could be the front seat. Maybe our research are the side mirrors. They're all necessary parts of the final car, some of them arguably more important than others. And on that note, I'd just like to give you 2 more pointers in case you would like to learn more and you found this interesting. Obviously, there's lots of nuance I couldn't cover in the space of 1 hour, but we have this great resource, algo-reasoning.github.io, which covers a 3-hour tutorial, slides and code, annotated references, which should hopefully help you get started in this area if what I said sounds interesting. And if you come from combinatorial optimization, we also have a 58-page survey that shows how graph nets can be used in general operations research, supply line, and combinatorial problems, with section 3.3 talking specifically about the stuff we discussed today. And finally, to wrap up, if you remember, we started from a curious and consequential question that a typical undergrad competitive programmer might ask, and we arrived at something that might help us in the future to build generally intelligent systems. I like to think neural algorithmic reasoning is here to stay, and if you want to chat about it, its implications to AGI or otherwise, please do reach out either if you have any questions now, or you can also reach out to me via email. And I must mention at the end, it really takes a village. Like, all of the papers I mentioned here were a part of my work, but also work of all of the fantastic people listed on this slide. I don't even think this is everyone I collaborated with on this stuff, but it's the most, I guess, relevant group of people. So thank you all once again, and thank you again for inviting me. I hope you found it interesting. Thank you so much.
Good. Yeah, thanks, Petar. I think it's been an amazing talk, really insightful. And I mean, it's amazing the amount of cool things that you have been doing. We have some time for some questions. If anyone has specific questions, feel free to write them in the chat. I can start maybe by one. And something interesting is this generalization in out of distribution. I think this is something quite important in these systems. And could you say maybe a few words about what can you do to maybe improve these methods in the out of distribution setting with respect to, I don't know, how you normally use machine learning methods? No, is there anything in particular that you do to robustify maybe these methods in that setting, or what can you do, because you will be mostly always evaluating them in settings that are slightly different from those in at training time?
Yeah, definitely. I mean, it is part of, say, let's go back to the first paper I mentioned, the neural execution of graph algorithms, where we say, I'll just give a simple example because there the math is really simple, like the choice to use the max segregation. We had some theory after that shows why this is the case, but basically, it says that when you have a ReLU MLP, right, it is a piecewise linear function. As you go sufficiently away from the training set, it turns into linear. So at that point, unless your target function is linear, you're screwed, right? Yeah. So basically, the only way to make ReLU MLP message functions work out of distribution is for your target is to set your neural network up so that the functions you learn are linear. And that is why the max segregation is so useful for fitting Bellman-Ford, because with max in there, it's a linear function that you have to learn. And also similar discoveries go on featurization. So say if you want to do n-body system tasks in physics, often there's like an inverse square law between the forces, right? So if you put R as your edge feature, that's really bad. If you put 1 divided by R squared as your edge feature, suddenly you get much better extrapolation performance because it's linear in 1 divided by R squared, right? So yeah, that's maybe just one simple example of a few inductive biases you can think of to get better out of distribution performance.
Good. Thanks. Let's see, we have one question. Have you tried using algorithmic complexity as an input? For example, find the simplest algorithm to solve a particular problem. Okay, so yeah, so maybe to incorporate maybe the cost now into the design of these methods.
So this is a very fun question. We haven't done it as a feature specifically, but what we have done is you can play with how many steps you iterate the processor for, right? So you can force the model to predict something in less or more steps. And there are some remarkable things that can be found there, in that you can often find solutions that are equally or closely good when you have maybe half the steps that the theoretical algorithm would have to take. And there's a very good reason behind this. And I think there could be some exciting potentials for computer science as a result. A lot of these algorithms that we tend to use traditionally were designed in the 60s, 70s, right? When the main model of computation was a single-threaded CPU. But these GNNs aren't limited by that. They can look at all the nodes at once and do execution in parallel. So they might be able to discover something that fits the same function, but in a more efficient manner. And maybe in the future, this might lead to new parallel algorithms being discovered for GPUs. So yeah, we haven't explicitly added complexity as a signal, but forcing the model to solve something in fewer steps than what the algorithm would require, we have done that, and it has led to some very interesting findings. Maybe in the pointer graph networks paper, you can see one simple example of this, but yeah.
Good. Thanks a lot. I think we are out of time. So yeah, thanks, Petar. It's been really great to have you here, and hope to see you soon around in Cambridge at some point. Thanks.
Okay. Thanks for
Bye,
having me.
everyone.